Okay, so now we're going to do closed pipes part 2. And in this situation, it's going to be a little different. What we did before was we had a single frequency of sound and a single wavelength of sound. And we were seeing what different lengths of pipe, what different lengths of pipe will resonate with that specific frequency. Okay, well, now what we're going to do is we're going to do just the opposite. And you know what? I'm going to try this on the... I've got this pipe right here. And here's this PVC pipe. Okay, let's zoom all the way out so you can see it. And what I'm going to do is, by holding it fixed, I'm going to put my hand on the bottom end, and here's the top end, and I'm going to blow across it, and it makes, here's the first frequency that will resonate with that length of pipe. And then, if I blow harder, I can get another frequency. And then if I blow even harder, I can get another frequency to resonate. Okay, so you heard those 3 different frequencies that resonate with that pipe. And so what we want to know is, if I hold the length of pipe fixed, what are the different frequencies that will resonate in that pipe? So we're going to have, let me go ahead and zoom in here. So we have the same situation. We have twice the length of the pipe. Is, the sound has to go down the pipe and reflect off the closed end and then back up to the open end. So it's still going to travel 2L. But now we want the longest possible wavelength. And that's still going to be the wavelength over 2. Okay? But now the wavelengths are going to change. So I'm going to call that wavelength 1. And so this is going to be the longest wavelength, and therefore the, shortest wavelength. Anyway. So now when I solve for the wavelength, I get the wavelength is equal to 4L. And now, I want to express this in terms of frequency, though. What frequencies are going to resonate in this? So I know that the wavelength is equal to the speed of sound divided by the frequency. Wavelength equals velocity of the speed of sound divided by the frequency of the sound. It'll give me the wavelength. And I know that that's going to be 4L. So now I can solve for F1. And I can say that F1, I ran out of room here, F1 is equal to the speed of sound over 4L. Okay, well, what if the wavelength was shorter? So this is the lowest possible frequency. This is the lowest frequency that will resonate in that pipe. Okay, now, what if there was a shorter wavelength? What if the wavelength, what if the length of pipe was actually equal to 3, instead of half the wavelength? Let's take a look at this equation right here. It was this, except now I'm holding the length fixed, and I'm going to call this lambda sub 2. So 2L is equal to 3/2 the wavelength. So actually I'm using this one right here. So it will resonate if twice the length of the pipe is equal to 3/2 of the wavelength. Well, if I go through the same analysis here, if I solve this for the wavelength and then the frequency, you will see that if you get F2 is equal to 3V over 4L. So just take this, make the substitution like I did before, and you'll get this. And this shouldn't be too surprising because, let me make some more room there. This is 3V over 4L. You'll see why I erased it in just a second. Because what is V over 4L? V over 4L. That's the first frequency that will resonate. So the second frequency that will resonate will be 3 times the first frequency. And then I go back to the third one. Well, I know that 2 times the third length will be 5/2 of this. Well, instead of doing that, I'm going to keep the length fixed and then solve for the wavelength. So 2L is equal to 5/2 of the wavelength. This is wavelength 2 over here. This is wavelength 3. Well, let's just go ahead and do the math here. This is going to be equal to the velocity of sound over F3, the third frequency. So solve for the frequency. You get F3 is equal to 5 times the velocity over 4L, which is equal to 5 times F1. So when I blew through this pipe, here's F1, here's F2. Now F2 there was 3 times the frequency of F1. And then F3, here's F1, F2, F3. Okay, that's 5 times the frequency that I started with. I'm afraid when I play this, it's going to blow out my speakers. We'll see. So we can see that F sub n, the frequency of sound that's going to resonate, is going to be the odd numbers times F1. Well, that's 2n minus 1 times F1. But F1 is the velocity over 4L. So here is the equation that we would use. If I know the length of my closed pipe, and I know the speed of sound, I can use this equation to find all the frequencies that will resonate in that closed pipe. Now this makes sense, because let's zoom all the way out so we can see the whole paper here. Here we have the equation. Thank you. Here we have the equation where if the frequency is held fixed, these are all the different lengths of pipe that I can get to resonate with that specific frequency. But if I just switch this L sub n with, bring F out here and L sub n over there, and then put the n subscript on the frequency instead of the length, I get this. Okay? And so these are the things you're going to need to know. And this is all in combination, of course, with the speed of sound equals the frequency of the sound times the wavelength of the sound. So you will use these two, or this equation if you're solving for different lengths, this equation if you're solving for different frequencies, or if you want to express this in terms of wavelength instead of length or whatever, you can do that. So you can use these 3 equations, this one, and this one, to solve any closed pipe problem that I'll give you. And it all works together. That is all.